Hello, I'm going to continue to talk about energy stores and energy transfers in this video. I started it in the last video. In the last video, I made it clear that the old model of energy types and energy transformations shouldn't be taught anymore at key stage 3 or key stage 4 or any stage actually. That wasn't to say that it was a bad model. The idea of chemical energy being transformed into kinetic energy or transformed into electrical energy, or transformed into sound energy. Those models can work, but they have been succeeded perhaps, by this newer model. Actually, I don't think it is newer, but it certainly seems newer in education. The model of energy transfers and energy stores. And sometimes energy transfers are called pathways. I have seen that terminology used. I don't like it myself. So energy stores, let's start with some of the obvious ones. If I take a ball like this, I don't know which one shows up better in the camera. If I take a ball like this and I lift it up, I'm pushing it and I'm moving it through Earth's gravitational field. As it ascends, energy is stored in the ball's gravitational potential energy store. No real difference to energy types there. This is where the problem comes in, of course, because there's some overlap. So as I lift up this ball, I am doing work on the ball. And actually what's happening is as I push this ball with a force, I am actually putting energy into the kinetic energy store of the ball. That's what the force is doing. It's doing work on the ball, increasing the energy in its kinetic energy store. But actually, as I push it, there's also the force of gravity acting on it in the opposite direction. So as I push this up, because it's moving at a constant speed, happens to be that I'm pushing at a constant speed, then the force I'm applying is equal to the force of gravity acting on it. That's why the velocity isn't changing. What that means is that the force that I'm exerting, the push force from my hand, which is transferring energy into the kinetic energy store of the ball, at the same time that's happening, the gravitational force is moving energy out of the kinetic energy store of the ball. And if I'm pushing it, moving at a constant speed, the rate that energy is going into the kinetic energy store of the ball because of me pushing it is equal to the rate that energy is coming out of the kinetic energy store of the ball and going into the gravitational potential energy store of the ball because of the force of gravity. You see why it gets complicated. Now, if I don't push it up, if I just throw it up and then let it coast up all by itself, you notice it slows down, stops, and then speeds up. The only force acting on it in the case where it's going up, slows down, stops, and then comes back down again, the only force acting on it is the gravitational force. And the gravitational force is acting down on it at all points, and the gravitational force is removing energy from the kinetic energy store and moving it into the gravitational potential energy store, and then when it descends, it's moving it from the gravitational potential energy store into the kinetic energy store. But energy isn't a substance, it's not a fluid. There isn't something actually flowing between these stores. We use the concept of energy stores as a model. Actually, the amount of energy in our system, which is the ball moving up, stopping, and then coming back down again due to the Earth, the amount of energy is fixed. It's an accountancy system. That's what energy is. And it just so happens that the amount of energy, however we calculate it, doesn't change. And we could go into detail about Nernst's theorem and time symmetry, but I don't think we need to do that. We can just accept or understand that energy is conserved. So what we talked about there is forces moving energy between two stores. And one of those stores, the kinetic energy store, was associated with the movement of this ball. And the other store, the gravitational potential energy store, was associated with the position of this ball relative to Earth's gravitational field. Now I can take an example, like for example these two balls, and I can have a look at energy being transferred from a kinetic energy store of one ball to the kinetic energy store of the other ball due to a force. If I roll the red ball towards the yellow ball, when they collide, energy is transferred. Actually, not all of the energy was transferred because the red ball continued to roll. But the yellow ball started to roll. The yellow ball gained motion. The yellow ball had its kinetic energy store increased. And there are two stages to this. As this one comes in like this, what's happening? Well, the yellow ball pushes the red ball that way. And when the yellow ball pushes the red ball that way, it is producing a force in the opposite direction to the momentum of this ball, which means that the ball, having work done on it, reduces its kinetic energy, loses its kinetic energy, it slows down. And if I managed to get it perfectly lined up, it would actually stop if there was no spin and all the other fun things that happen in billiards. So this ball moving like this, colliding with this ball is being pushed with a force that way, which means this ball's kinetic energy store reduces. At the same time, this ball is being pushed that way. That's Newton's third law. The red ball is being pushed that way at the same time and with the same magnitude force along the same line of action, the same type of force, the yellow ball is being pushed that way. So these forces are a pair. And the yellow ball, which initially is stationary, is being pushed this way, which is why it gains velocity this way and why its kinetic energy increases. Now, we still talk about transfers. We still talk about the kinetic energy of the red ball being passed to the kinetic energy of the yellow ball. We still think about it in those terms, and that's okay. But energy is not a substance. There isn't anything actually flowing from the red ball to the yellow ball. All that's happening is the kinetic energy store of the red ball is decreasing, and it just so happens that the kinetic energy store of the yellow ball is increasing at the same rate for the same amount of time, so that the amount of energy the red ball loses is the same as the amount of energy the yellow ball gains. So that's what forces are doing. Now, I've talked about two energy stores so far. I've talked about gravitational potential energy due to position in Earth's gravitational field, and I've talked about kinetic energy due to the motion of an object. But there are three other energy stores. And I've talked about one transfer mechanism, forces, but there are three other transfer mechanisms. So let's explore some of those in a little bit more detail. When it comes to thermal energy, there are two ways that energy is stored in a body as thermal energy. One is due to the motion of the particles within that body. They're all jiggling around, and there'll be an average speed of that jiggling. And if you increase the temperature of the body, you increase the thermal energy store because the particles jiggle more. And at the fundamental level, it's the particles' kinetic energy, all added together and averaged across them, and some other fun factors to do with how many ways in which the particles can jiggle, but we'll push that under the carpet for now. It's the motion of these individual molecules, particles within the matter. It's the motion of them that is associated with temperature. They move faster on average, it's a higher temperature. And so we increase the thermal energy store. What we're actually doing is increasing the average kinetic energy of the particles or the molecules inside that substance. There is another way that we can increase energy in the thermal energy store, and that's by changing the state of the substance. Now, in the case of changing from a liquid to a gas, in a liquid, our molecules, I will say particles and molecules interchangeably. Particles just the smallest unit of a particular type of matter. So the particle of nitrogen gas is a molecule of nitrogen, whereas the particle of helium gas is an atom of helium. So the particle of a cathode ray is an electron. So I'll just use the word particles or molecules for this context. Interchangeably is fine. So in a liquid, they can move past each other. These molecules, these particles, can exist in different positions relative to each other as they flow around each other. But they still have to be quite close together. And with a gas, these particles can be moving at the same average speed, but they're now much further apart. The particles, the molecules are able to leave and move around in 3 dimensions quite freely. So what's happening there? Well, in a sense, what we're doing is changing the relative position of the particles from each other. That's what we're doing when we change state. And that's actually exactly the same thing that happens in chemical energy stores as well. When a chemical reaction takes place, we are moving charge. That's all we're doing, we're moving charge. And we're moving charge through an electric field. And so what we're talking about there is relative position of charged particles, ions, electrons, relative position of those relative to an electric field. So it's no different to gravitational potential energy being associated with the position of mass in a gravitational field, the chemical energy, and for this part of thermal energy associated with state changes, it's just the position of charges in an electric field. So that's why I've got this thing here, which I'm just going to fire up and show you. Let's just move these out the way for now. What we've got here is my Van de Graaff generator. It is a handy way of producing strong electric fields. And if I turn it on, hopefully the noise isn't too interfering. And get some sparks, ooh and ah and such, ooh and ah. But here I've got a small tin foil ball on a piece of string. Now, at the moment it's neutral, but if I charge it by allowing it to come into contact with the Van de Graaff generator dome and then move it away again, the dome and the little tinfoil ball are now the same charge. As I move the tinfoil ball towards the dome, you can notice it is repelled. Its position relative to the dome of the Van de Graaff generator is repelled. It keeps swinging back. Maybe it's discharging somehow. It does look like it's discharging in the air. Maybe this isn't a very good ball. Maybe it's got some sharp, jagged points. But it's repelled by the dome. There we are. That's quite nicely done. That's repelled by the dome. You can see that because the string is at an angle. I'm moving it closer and the ball isn't getting as close as you think it would. So what's happening here? Well, as the ball moves towards the dome, and they're both at the same charge, there's an electrostatic repulsion. And the closer they are together, the more energy is stored in what we might call the electric potential energy store. Ah, that's not one of the 5 that we listed, but it's there, electric potential energy store. And it's effectively this electric, let's turn it off here, it's effectively this electric potential energy store that causes the change of state part of the thermal energy store and changes in chemical energy stores as well. So it's just position in a field. That's all that is. That's the physical manifestation of what we call chemical energy or that particular part of thermal energy. But what about elastic potential energy? So take a rubber band and stretch it. Well, what happens when we stretch it is we're aligning the molecules. We're making the molecules that are all tangled up nice and straight. But why were they tangled in the first place? The molecules were tangled because they're constantly being bashed by other molecules within the rubber. So as I stretch it, I'm changing the relative position of these molecules from being all coiled up because they're being bashed to being stretched out. They're still being bashed, which means that they still are being pushed to come back together. So that is no different to what's happening here. It's just forces. There's just particles colliding with the long chain molecules in the rubber. And that's trying to pull it back together. That's what's happened when there are those collisions. I use the word trying to, and it's anthropomorphizing the physics, but it's okay for this. So as I stretch this, those molecules, those cross links are still colliding with the long chain polymers. And when I remove the force from my finger, they cause the molecule to coil up again. So elastic potential energy, I suppose, is a combination of energy stored due to the position of the molecules, whether they're stretched out or whether they're all coiled up, and kinetic energy, the kinetic energy of the cross-linked particles colliding with them. And so what force is it that causes the contraction of the rubber band? I guess it's no different to the force between these two balls. It's collisions. It's just that sort of same force. So much for elastic potential energy. So now we've had a look at thermal energy and we understand that that's to do with motion of particles and to do with relative position of particles. We've looked at kinetic energy of macroscopic things like this, potential energy, gravitational, we've added electrostatic into the mix as well, elastic potential energy, and I think we mentioned chemical energy as well. We've got the lot, but of course that leaves sound, light, electricity. It leaves them to one side. We haven't covered them yet. We've mentioned electrostatic potential energy, yes, but that's not the same thing as electrical energy as thought about using the older model, which is still taught by some schools, most schools, by some teachers, most teachers. And in revision guides, I've seen it in revision guides still, even though it's not part of the current curriculum. So how are we going to make sense of this? Well, remember that with this picture here, we had an object that was physically moving, exerting a force on another object. And there was an energy store of one object reduced because of that force, and the energy store of the other object increased because of that force. And ultimately, that was what was happening with all the different stores and transfers we've talked about. So let's have a think about waves. And let's start with a simple wave on a spring. If I take a slinky and I produce a wave on this slinky, like this, I'm not sure whether you'll be able to see that, so let's do this sideways. A wave, you can hopefully see that there is a compression moving down this wave. Now what's happening in that compression? Well, in that compression, a bit of the spring is being bunched up. As it's being bunched up, it is experiencing less of that stretching force, and that means there's more stretching force of the two bits of spring either side of it. And it's that force that's causing the stretched part and the compressed part, what we call the rarefaction is the stretched part, what we call the compression is the squashed part, to move along the spring. It's ultimately no different. It's just collisions. Because remember, the reason why the spring is elastic at all is the same reason on my rubber band. Where's my rubber band? There it is. The same reason that the rubber band is elastic. It's because of collisions between molecules. It's all the same thing. But there's an important difference here in that the spring molecules themselves don't get transmitted from the start to the end. So there's no transmission of an object from A to B transferring that kinetic energy. What's actually happening is each bit of the spring pushes on the bit next to it. What we mean by wave is that process, and there's all clever ways we can describe it mathematically, but that's what we mean by a wave, is that process. In itself, the wave isn't a thing. All there is relative position and relative motion of matter. That's what we see here. Now, I've obviously shown a longitudinal wave because it's easier to explain that way. Transverse waves actually work exactly the same way. It's just slightly more complicated in describing what the forces are doing. But it's the same thing. It's just relative position and relative speed and collision forces transferring the energy. Well, that's a wave like this. What about sound waves? Well, in sound waves, the air molecules are moving at, 450, 500, maybe even faster, 500 meters per second. That's how fast they're moving. But what's actually happening is that the air pressure is going to be varied. So the air gets bunched up. The particles moving all over the place. But because of drift, there's areas where there is higher density and areas where there's lower density. That's what sound is. And so ultimately, it's no different to what's happening here. It's just what the medium for the wave is air pressure variance rather than density of spring variance. But it's still just forces causing changes of position and changes of movement, changes of speed, changes of velocity. Well, okay, so much for sound. What about light? Now, this is where it gets complicated. And the reason why this new model is a superior model, because unlike with sound, where there is matter, and the waves on the spring, where there is matter, light And I'm including all parts of the electromagnetic spectrum in that, whether it's visible light, infrared radiation, which you might call heat. I try to avoid that term as much as I can, because I don't want you to confuse heat with thermal energy store. So infrared radiation, visible radiation, but also things like X-rays or radio waves. Every part of the electromagnetic spectrum, there isn't actually any matter moving. And that's where the new model becomes really, really useful. Because we can't jump into some point in the middle of the transmission of electromagnetic radiation and see particles shaking around and pushing on the particles next to them. Now, with sound, we can do that. With the spring, we can do that. We can zoom in, we can have a look, we can pause time, we can have a look and say, okay, that particle has more kinetic energy than the particle next to it, but they're going to collide and transfer that energy. But that's not the way it is with electromagnetic radiation. The electric fields that are varying cause varying magnetic fields, which cause varying electric fields, which cause varying magnetic fields, and so on and so on and so on. But the fields themselves don't have tangible existence. They're not particles. It's not matter. It's not a substance with mass. There's no kinetic energy that's being transferred from A to B when there's an electromagnetic wave passing from A to B. It's not that at all. Now, we can describe what the fields are doing mathematically, and it's a wave equation, so we refer to these things as waves. But they're not physical. And so to say energy stored in the wave would be a nonsense, because there's nothing to store the energy. You can't say the fields store the energy, because the fields are constantly changing. Otherwise, it wouldn't be electromagnetic radiation. If I just have a big electric field and it doesn't vary, then there's no transmission of energy from A to B by that big electric field. That's not how energy transfer works. We need to have something moving. So let's imagine this is an aerial, maybe transmitter of electromagnetic radiation, and this is a detector, an antenna. Well, maybe in this one I've got electrons shuttling up and down, and that causes a varying electric field, which causes a varying magnetic field, which causes a varying electric field, and so on. And that electromagnetic radiation ripples out, and in my detector, my electrons get pushed up and down by that varying electric field. Now here, I have the electrons moving. So I could talk about the kinetic energy of the electrons, and because they're in an electric field, just like with my little tinfoil ball, where it got pushed against the Van de Graaff generator because it was in an electric field, those electrons shuttling up and down are going to be pushed by those electric fields. So there's going to be potential energy, electrostatic potential energy stores, and kinetic energy stores for these electrons. And likewise at the other end, but not in the middle. That's the key idea. We don't store energy in the wave and then deliver it here. The energy that's here gets, the energy store that's here reduces. And the energy stores that are here increase. And it is the wave that's transferring the energy that's causing this energy store to reduce. That's the emission of waves. And that's causing this energy store to increase. That's the absorption of waves. But the waves themselves are not an energy store. It's complicated, but it makes a lot of sense. Okay, so that's electromagnetic radiation. What about electricity? Well, in electricity, as I've already said, we've got to have electrons shuffling around to actually have the energy transfer. In electricity, that's no different. You've got to have electrons moving for energy to be transferred within a circuit. That means you've got to have a current. So actually, when we say energy transfer by a current, it is no different than energy transfer by an electromagnetic wave. Just like when we say energy transfer by heating, by which we mean conductive heating, it's no different than energy transferred by forces, because conductive heating is just caused by molecules colliding with other molecules. It's no different. Energy transfer by conductive heating is energy transfer by forces. Energy transfer by a current is the same as energy transfer by the emission and absorption of electromagnetic radiation. which ultimately what's happening is the charges are feeling forces. So it's no different. Waves, as a method for transferring energy, is still energy transfer by forces. And the other one, what we've got conductive heating, we've got waves, we've got current, we've got forces. We've covered them all. They're all just forces. And so can you see that actually, if you understand the newer model of teaching energy transfers and energy stores, it reduces the idea of energy down to just two bits: potential energy because of position and kinetic energy because of movement. And that leads quite nicely on to understandings of Hamiltonian mechanics, of using things like Lagrangian mechanics, the Euler-Lagrange equation. The more advanced methods of solving physics problems, which we learn about in the first and second year of university, immediately flow on from the same energy models that we want to get you to understand right from the start. And as long as schools are teaching that energy is transformed from one type to another, then that bit of information is going to be missed. I hope that was useful. And I'm hoping these props really helped you to get a feel for what's going on here. Remember those 5 energy stores: kinetic, gravitational potential, elastic potential, chemical, and thermal. And remember those energy transfer methods: forces, conductive heating, waves, and currents. Those are what you need to know for your GCSE. There are others. I've already mentioned a few others. There are others. But they ultimately boil down to the same things. Forces, that's all that transfer is, and energy stored by virtue of position or movement. That's it. Now, what's really going to mess your head up is when we get into relativity in year 13 and at university physics, movement and position aren't actually any different either. You're not ready for that yet.